So hello everyone, welcome to Chem Analysis. In today's discussion, I will solve previous year CSIR-NET December 2018 Inorganic Chemistry questions, and that questions are for 2 marks. Here I will discuss or solve 10 questions. Previously I have uploaded 3 videos for the question answer discussion of previous year CSIR-NET December 2017 questions. If you have not watched that video till now, I will give the link in the description box. If you want to watch, then you can go through the given link. So let's start this discussion. The first question, we can see that all the questions are for 2 marks. The first question, we can see that we have to tell about the order of acceptor ability for these phosphorus ligands. And in all the phosphorus ligands, phosphorus center abstract or accept electrons in its vacant 3d orbital. Now higher the electron deficiency on the phosphorus center, higher will be its electron acceptance tendency. Now electron deficiency or electron density on the central phosphorus atom will depend on the electronic property of the attached group. Now if we see the electron withdrawing tendency of the different four groups attached to the phosphorus center, then the order will be fluorine will be most electronegative, so it will abstract electron density from the phosphorus center more. After that it will come OPH group, then pH, and at last methyl will be more electron releasing. Therefore electron deficiency on the phosphorus center, that is on the different ligands, will follow the order, that is PF3 will be more electron deficient if we tell about the electron deficiency order. You can also think the order of electron density. The order of electron density will be just opposite to the electron deficiency order. So electron deficiency of PF3 will be highest, later it will come POPH whole 3, then PPH3 whole 3, and least electron deficient will be PME3 whole 3. Now as I said before that higher the electron deficiency on the central phosphorus center, higher will be its electron acceptance ability. So order of electron acceptance will be PF3 will show highest electron acceptance order, then it will be POPH whole 3, then PPH3, then PME3. So among the given 4 options, we can see that option number B is the correct answer. This question was asked from phosphorus NMR, and for phosphorus and fluorine NMR I have already uploaded a video where I have discussed many different type of phosphorus and fluorine NMR related questions. If you want to watch the video, I will also give the link in the description box. Here it is asked that in the phosphorus NMR within the bracket is 1H, that means it is proton decoupled phosphorus NMR of a diametric complex MPr3 whole 3 Cl3. M is a transition metal for which I is equal to 0. That means for the metal center there will be no coupling for the phosphorus center, since I is equal to 0 for the metal, and NMR active nuclei should have I is greater than equal to half. So here we have to identify the number of expected resonance for this complex. If we draw the structure of this complex, that is it is meridional Ma3B3 type complex. That means in meridional the 3 PR3 ligand plane and 3 Cl3 ligand plane will be just perpendicular to each other, and in facial the plane containing the 3 PR3 ligand and 3 Cl ligand will be just parallel to each other. So if we write here PR3, So we can see that the plane containing these 3 Pr ligand and metal center is just perpendicular to the plane containing these 3 Cl ligand and the metal center. And in this complex, in phosphorus NMR, we can see that these two phosphorus ligand Pr3 ligand are equivalent, and this is different to these two Pr3 ligand. So these two Pr3 ligand will give one peak, one resonance, and this Pr3 ligand will also give another resonance. So as a whole there will be two resonance in this meridional complex. You can try to solve for the facial complex what will be the number of resonance in the facial MPr3 whole 3 Cl3 complex, and that I have also solved in my previous video. To get the solution you can watch that video. This is a time consuming question. Here we have to tell about from the given given 5 compounds, we have to tell about the paramagnetic species and the EPR inactive species. That means paramagnetic species means the compound or molecule should contain unpaired electron, and if the molecule contains unpaired electron, that will be also EPR active. And EPR inactive means the molecule does not contain any unpaired electron. So if you see the electronic distribution for these different complexes, for the first complex NO, the valence electron for NO is nitrogen will contribute 5 valence electron and oxygen will contribute 6 valence electron. Therefore there is 11 valence electron, and this electron number is odd, and if we distribute this 11 electron in the molecular orbital of NO, we can see there must be one unpaired electron, at least one unpaired electron. Since the total number of valence electron is odd, that means there must be one unpaired electron, and this will be paramagnetic. The species containing unpaired electron should be paramagnetic, and if it does not contain any unpaired electron, then it will be diamagnetic and also EPR inactive. For the second case I2, the number of valence electron in this case will be 14, and if you distribute this 14 electron in the molecular orbital of I2, there will be 2 electron in the bonding molecular orbital, and other 12 electron will be remain as non-bonding electron, and they will all be paired. So there will be no unpaired electron. Since the total number of valence electron is even, it does not mean that even electron means there will be no unpaired electron, since oxygen is also containing even number of valence electron. But if you distribute the electron in the molecular orbital, then you will see that there is unpaired electron in pi star orbital. So there will be no unpaired electron, and therefore it will not be paramagnetic and also EPR inactive. So here we have to tell about the number of paramagnetic species and the EPR inactive species. That means I2 will be EPR inactive, and for I2 minus, the number of valence electron is 15, and that is odd, so there must be one unpaired electron, so it will be paramagnetic. And for Cu2 plus number of valence electron, Cu2 plus means it is D9 system and it is odd, and if you distribute the electron in the d orbital, there will be one unpaired electron, so it will be also paramagnetic. And VO2 plus, in VO2 plus, the vanadium center is here will be O is 2 minus, so vanadium center will be in +4 oxidation state, and in +4 oxidation state vanadium will be scandium, titanium, vanadium, that means it will be D1, and that means it contains one unpaired electron, so it will be also paramagnetic. Therefore we can see that NO, I2 minus, Cu2 plus and VO2 plus is paramagnetic, and number of paramagnetic species is 4, and I2 is EPR inactive. So option number B is the correct answer. It is just a lengthy question but very easy question. Now here we have to identify the correct statement, or multiple correct statement may be possible. We have to identify the correct statements for this BH3CO complex. The first option is sp2 hybridized orbital of boron accepts the lone pair of carbon monoxide. Now in BH3 the boron is sp2 hybridized, and all the 3 sp2 hybridized orbital form 3 sigma bond with 3 1s orbital of hydrogen atom, and there is one p orbital that is vacant, and in this p orbital carbon monoxide can donate a lone pair electron. So BH3 will abstract a lone pair electron from carbon monoxide in its vacant p orbital, not sp2 hybridized orbital. So first option is not correct. It's new CO, that means CO stretching frequency value is more than that of free carbon monoxide. Now here we can see that since carbon monoxide is donating lone pair electron in vacant p orbital of boron, that means electron density within the carbon monoxide molecule decreases. If you see the molecular orbital diagram of carbon monoxide, you can see that with decreasing the electron density from the carbon monoxide molecule, the stretching frequency of carbon monoxide increases. That is, as the electron density decreases, stretching frequency increases. Therefore we can say that option number B is the correct answer, since in this complex new CO will be higher than that of free carbon monoxide. And for the third option we can see here that formal oxygen state of carbon is +4 in this compound. In this BH3 CO complex, oxidation state of carbon is +2, not +4. Is it okay? So this option is also not correct, and we can see that option number B is the correct answer. Only this option is correct. Here oxygen state of carbon. Here we have to tell about the strongest acid and strongest base among these 4 compound. And here I want to mention one thing, that the acidity and basicity order we have to tell, that is for Lewis acidity and Lewis basicity. And for the given 4 option, we can say that PF5 and SbF5, since the fluorine atom attached to the central atom, so the central atom will be electron deficient and they will act as a Lewis acid. And in the other case, PH3 and SbH3, they will act as a Lewis base by donating the lone pair electron on the phosphorus or antimony center. Now first let's see the acidity order between this PF5 and SbF5. Now as we go from top to bottom, the size of the central atom, that is antimony, increases. Therefore size of antimony is higher than that of phosphorus, and due to this reason the incoming electron, since these two species will abstract lone pair electron or electron density, so the incoming electron will get more space to distribute for this antimony center, since the size of antimony is higher than that of phosphorus. So electron acceptance tendency will be higher for SbF5 than that of PF5. So acidity of SbF5 will be higher than that of PF5. So SbF5 will be strongest acid. Now between basicity, here phosphorus center is smaller in size, so the electron density on the phosphorus center will be higher than that of antimony, since in antimony the lone pair electron is distributed around more space, so it will be reluctant to donate the lone pair electron to another species. So electron donor tendency will be higher for PH3 than that of SbH3, and as a result we can say that basicity of pH3 will be higher than that of SbH3. Therefore pH3 will be strongest base, and among the given for the first option is strongest acid, so SbH5 is correct, and second is strongest base, so pH3 is correct. In this case also option number 2 is correct answer. So in this question we have to tell about the species which have zero dipole moment. Now to calculate the dipole moment we have to first know the structure of the compound. For SiCl4 it is tetrahedral in geometry, that is shape of this compound is also tetrahedral, and in this case the dipole moment corresponding to this 3 SiCl bond will be just opposite to that of SiCl this bond. In this case dipole moment will be directed in this axis, and in this case dipole moment will be directed on the opposite axis. And as like CCl4 or CH4, we know that the dipole moment corresponding to this SiCl3 is equal to the vector summation of this 3 mu SiCl will be just equal to mu SiCl, and the direction of this SiCl3 or mu SiCl is in this direction, and there is another dipole moment generating due to polarization of this silicon and chlorine bond, and that dipole moment is just in opposite direction, and since it is also for mu SiCl, so they will cancel it out, and the net dipole moment for this molecule will be 0. Is it clear? It is just like CCl4, as in CCl4 the dipole moment corresponding to mu CCl3 will be just opposite to mu CCl, so in CCl4 the dipole moment is also 0, and in this case also since the geometry or shape is tetrahedral, in this case also mu will be 0. And PoCl3 the geometry is also tetrahedral, and the resulted dipole moment corresponding to this 3 PCl bond will be in this direction, and the dipole moment generated for this PO bond will be just opposite direction, and since the value of this two dipole moment is not same, so the dipole moment corresponding to this PoCl3 molecule will be not equal to 0, it will contain some dipole moment. For the NF3 case, its shape is pyramidal, that is geometry is tetrahedral, and since it is containing one lone pair electron, so shape will be pyramidal. And in this case the resultant dipole moment corresponding to this 3 NF bond will be in this direction, and the dipole moment corresponding to this nitrogen lone pair will be in this direction, though the dipole moment will be very less, and the resulted dipole moment will be in this direction, and it will be not equal to 0. And for the last case, trans SnCl4 Py, that means it will be octahedral complex, this is trans complex since two Py ligands are in trans direction, and in this case the dipole moment corresponding to this SnCl bond will be cancelled out by this SnCl bond, and similarly the dipole moment corresponding to this SnCl bond will be cancelled out by this SnCl bond. So for this SnCl4 moiety the dipole moment is 0, and similarly the dipole moment corresponding to this SnPy ligand, that is SnPy linkage, will be just in opposite direction to that of this SnPy linkage, so this dipole moment will be also cancelled out, and net dipole moment will be 0. So we can see that SiCl4 and this trans SnCl4 Py whole 2 shows 0 dipole moment, so option number C is the correct answer. This question is very easy question. It is asked that the standard reduction potential in acid medium for this 4 species. Now we know that higher the reduction potential, that means higher will be the tendency for the species to get reduced. That means higher the tendency of a species to abstract a electron, higher will be its standard reduction potential. Now among these 4 species, the electronegativity order will be fluorine will be most electronegative, then Cl2, then zinc, and the least electronegative will be sodium. Higher the electronegativity, higher will be its tendency to abstract a electron. That means higher will be its reduction potential. Therefore, the order of reduction potential, that is standard reduction potential, will be just this order, that is fluorine, then Cl2, then zinc, then sodium. It is just depending on the electronegativity or electron abstracting tendency of the element. So we can see that option number B is the correct answer. Here we have to this question is from molecular orbital, and here we have to tell about the LUMO, characters of LUMO for cyanide and O2. Now if we see the molecular orbital diagram, that is molecular orbital electronic distribution for cyanide minus, in total carbon contains 6 electron and nitrogen 7, and there is 1 anion. So there will be 14 electron distributed in the molecular orbital, and since it is containing 14 electrons, so the molecular orbital distribution, that is electronic distribution in the molecular orbital, will be according to the less than equal to 14 electronic configuration, and the electronic distribution will be like this: sigma 1s2 this star means antibonding, then pi 2p y, it will be u, and pi 2p z, it will be u, then it will come sigma 2px g, since here is 4, 6, 8, 10, 12, and it is 14, and after that it will come pi 2py g star. They will be similar energy, these two pi orbital, pi 2p z g star, and at last there will be sigma 2px u star. So here we can see that for the cyanide ligand, the characteristic for LUMO is this pi star 2py and pi star 2pz, and therefore the characteristic is pi g, and since here it is given as pi u pi g, so the LUMO for cyanide will be pi g characteristic. And for O2, since O2 will contain 16 electron, so all the distribution till this will be similar. After that, since it is belonging to greater than 14 electronic distribution, so after sigma 2s u star, there will come this sigma 2px molecular orbital. It will be 2, then it will come pi 2py u 2, pi 2pz u2. Since it is here there is 8 electron, it is 10, 12, 14, and there will be distributed 2 electron in the pi star orbital, and since pi star orbital are same in energy, so there will be unpaired electron in both the pi star orbital. There will be 1 electron, and the last there will be sigma 2px star, and it will be u. So we can see here that the LUMO for this oxygen molecule will be sigma 2px u star, that means sigma u. Since according to the option we can see that it is only given G-rad and un-G-rad, so here we are just writing G-rad and un-G-rad. So we can see that option number C is the correct answer for this question. This is a very easy question. We have to tell about the electronic configuration for the metal ion in octahedral coordination, which will show strong Jahn-Teller distortion. Now, from the rule of Jahn-Teller distortion, the electronic configuration which will contain Eg orbital unsymmetrically filled. That means the Eg orbital will be less than or more than half filled, not half filled or full filled. Unsymmetrically filled. So it will show strong Jahn-Teller distortion, strong JT distortion. And if the T2G orbital is unsymmetrically filled, that is less than or more than half filled, then it will show weak Jahn-Teller distortion. In the T2G orbital unsymmetrically filled, it will show dynamic Jahn-Teller distortion, and if EG orbital is unsymmetrically filled, then it will show static Jahn-Teller distortion, that will be strong. So among the 4 options, let's first see the first option. Here it is T2G6 EG1. Since EG is unsymmetrically filled, it will show strong Jahn-Teller distortion. For the second one, here also EG is unsymmetrically filled, it will also show strong Jahn-Teller distortion. And for the third case, in this case also EG is unsymmetrically filled, since it is more than half filled. So we can see that option number A is the correct answer, since here all the 3 options, 3 electronic configuration is showing strong Jahn-Teller distortion. You can see the remaining option, you will see that one of the 3 electronic configuration will not show strong Jahn-Teller distortion. You can try to check the remaining electronic configuration to check that they are showing strong Jahn-Teller distortion or not. This is a question from inorganic reaction mechanism, and here we have to tell about the mechanism in which this cobalt NCS NH3 whole 5 2 plus and FeH2O whole 6 2 plus is converting to these 2 species by the intermediacy of this species. Now here we can see that the 2 reacting species are cobalt NCS NH3 whole 5 2 plus, that means here cobalt is in +3 oxidation state, and the other species is iron H2O whole 6 2 plus. Now since in the progress of the reaction there is a species that is identified or that is detected is iron HCN H2O whole 5 2 plus. This is a species identified in the reaction, and the final product is cobalt H2O whole 6 and iron H2O whole 6. Since the reaction is starting from this cobalt NCS species, and in the product there is no NCS ligand, and in the reaction medium there is a formation of such intermediate in which the iron species, in the starting there is no HCN ligand, but in the intermediate, that is during the progress of the reaction, there is a formation of iron HCN species. So we can think or we can say that there is a coordination of this NCS ligand from this cobalt center to iron center, and after the ligand transfer from this cobalt center to the iron center, there will be formation of such iron HCN species. And since here cobalt is converting from +3 to +2 oxidation state, and iron from +2 to +3 oxidation state, that means there is a electron transfer occurring, and the electron transfer is inner sphere, not outer sphere, since there is a coordination of the ligand from one metal center to the other metal center, and subsequent ligand transfer, and that ligand during the reaction is substituted by water. Since there is a coordination of the ligand and ligand exchange, so we can say that this electron transfer is inner sphere electron transfer, and we can say that this is a electron transfer since there is a change in the oxidation state of the two metal center, reacting metal center. So it is not interchange dissociative or interchange associative. This is a electron transfer, and the electron transfer is inner sphere electron transfer. Is it okay? If you feel any difficulty, then you can let me know in the comment section, or you can send me a mail as the mail ID is given in this video. This is the last question for this discussion, and it is a very easy question. Here we have to tell about the chelate ring configuration in the macrocyclic ligand in vitamin B12. Now in vitamin B12 the central metal center is cobalt, and it is in cobalt 2 or cobalt 3 depending on the ligand attached to the central metal, and the macrocyclic ligand is codeine ring. It is a cobalt codeine complex, and it is quite similar to the porphyrin ring as is observed in the hemoglobin or myoglobin where the metal center is iron. But the difference is that in the porphyrin ring there is 4 pyrrole ring, but in the codeine ring, that is in the macrocyclic ligand for codeine ring, there is 4 nitrogen containing ring, but that are not pyrrole ring. And along with that 5 member ring, in porphyrin ring there is 4 6 member ring, but in this case codeine ring there is 3 6 member ring, along with that 1 5 member ring. But in this case for porphyrin ring there is 4 6 member ring along with 4 pyrrole ring. So we have to tell this information, that is the chelate ring in this in the macrocyclic codeine ligand for vitamin B12, that is there is 1 5 member ring and 3 6 member ring. So we can see that option number A is the correct answer. So that's all for this discussion, and if you like this video then you can share it with your friends so that they can also know this important information. And if you are new in this channel then you can subscribe to my channel Chem Analysis to get such question answer series video in future. And in the next video I will solve physical chemistry and organic chemistry December 2018 CSIR-NET 2 marker questions. So thank you once again.